Okay, hello. I'm Austin Donnelly from Microsoft Research, and I'm here with my colleague Karin Strauss to talk to you about some very exciting new technology that we've been working on to store cold data, DNA and glass. So I'm going to use a hypothetical question to motivate this talk. How would you go about storing a Zetta-Byte of cold data? So there's no question that the amount of data in the world is growing year on year. The problem is that the amount of data that we can afford to store is not keeping pace with the amount of data we're generating. So really, what we need to do is lower the cost to store that data, to move that lower line up a little bit, and generate two new sorts of value from your data. You can either choose to store more data, or you can choose to store existing data for longer. Either or both of these things can work, and unlocking that extra value in your data is what we're trying to do with both these glass and DNA technologies. And we're thinking here about archival data. Most of the data over time is the very large back catalog that's important to the M&E community. And so we think of archive as data that's reasonably cold, and by cold I mean less than about a gigabyte a second per petabyte stored. So really, the title of my talk should really be updated. How would you store a Zetta-Byte of data at reasonable cost? So what sort of technologies do we have to help us here? Well, here I'm showing you a graph with a number of different technologies representing these bubbles. And on the x-axis, I'm showing you the latency of storing data in those technologies, from very fast on the left-hand side to very slow at the right-hand side. And on the y-axis, I'm showing you how hot the data you can store in those technologies, from hot at the top to cold at the bottom. And so in the top left corner, you have SSDs, which are well suited for blisteringly hot workloads. Then you move down to various hard drive technologies. This is where we store the bulk of our data in our data centers today. And at the far end, you've got tape, which has excellent economics, but very long retrieval times. So really, we need to keep attention and keep our eye on this retrieval time or latency metric. So really, the title of the talk should have been, how would we store a Zetta-Byte of cold data at reasonable cost and with reasonable access latency? So Microsoft Azure has solutions that we sell to our customers at each of these price points and latency points. But Karin and I come from Microsoft Research, where our mission is to expand the horizons and look further into the future than a typical product team can do. And so it's our remit to produce new technologies, to de-risk them to the point where a product team can take those on and turn them into a new solution for our customers. Now, we have some history in this space. Recently, we did a system called Pelican that fits roughly here in the technology space. So it's slightly faster than tape, slightly cheaper than bulk hard drives. So Pelican was a system that we developed where we connected thousands of hard drives to the data center network using the minimum amount of technology to try and keep the cost really low. We managed the complexity of this in software. And so Pelican is really our premier solution for getting the cost of data on hard drives down to minimum. So OK, maybe we can use Pelicans to store a Zetta-Byte information. What would that look like? Well, a typical hard drive is something like 15 terabytes. So to store a petabyte, you would need 67 of those hard drives. To store an exabyte, you would need 67,000 of those drives. And to get to our target of 1 Zetta-Byte, you would need 67 million hard drives. Clearly, this isn't actually a sensible thing to do. So let's go back to basics. What are our options when it comes to long-term storage media in the archive space? Well, we have magnetic media, such as hard drives and tapes. And we have optical media, for example, DVDs, CDs, Blu-ray. So hard drives, being a magnetic media, store the data using magnetic domains that are about 10 nanometers in size. And you can change the polarity of these magnetic domains to store your data. And tape is really just an offshoot of hard drives, except for the fact that the surface is incredibly large because it's stretched over this ribbon of tape. Optical storage records data by using pits and islands in 2 dimensions across the surface. And newer technologies like DVD will have somewhere between 4 to 8 layers, depending if it's single-sided or double-sided. So these are 2 alternative ways of storing media. But notice that none of those technologies really were invented after the cloud. All of them predate the cloud. And so they all baked in assumptions that are really not relevant in today's data center environment. So, for example, this is a typical hard drive. You'll notice that there are some drive electronics on the back. Okay? That means that every time you buy a hard drive, you also get the drive electronics, even if you're going to spin most of the drives down, and it's not going to get used. So that's extra cost that we could have had out of the system that we couldn't because of the way that the hard drive was designed to be standalone in a consumer PC. Right? That would be different in a data center environment. Okay, what about tape? Tape is great for a cost perspective, especially for cold archive data. Tape's wonderful. The problem is that there's half a mile of tape in this cartridge, and seeking through that takes some time. So it's quite hard to get low latency access to your data on tape. Optical discs have a habit of delaminating. I recently learned that in some cases, the polycarbonate layers, have a habit of going milky, and then you can no longer read the data. So what sort of media could we use? There must be a new media for a new era. And we're proposing glass and DNA as 2 such really exciting new media. So let me tell you a little bit about silica, and in a moment, Karin will tell you about DNA. So it turns out that if you want to store data for a very long time, there's no substitute to making permanent modifications to the media that you're going to write this on. And here I'm showing you a picture of a clay tablet that's in the British Museum in London. It's some of the oldest writing that has ever been found. It's about 5,000 years old, and it actually shows beer rations issued to workers in Mesopotamia. So some things never change. We do want to keep track of these important accounting things. But the point here is that this lasted 5,000 years precisely because they were durable modifications to the media. And the same is true of glass. Glass is this wonderful media. It's plentiful. We can make it cheaply from fused silica. It's very stable over time. We write it once, and you can read it many times. So it's naturally a worm media. Or in fact, we like to think of it as write once, read forever, because the data is incredibly durable, thousands to maybe millions of years. The data will certainly outlast me. And this makes it a really good fit for an archival media. The other thing is that magnetic media suffers from bit rot. Over time, we need to be continuously checking that the data that we have stored still is correctly held in our data centers. And so we have a process whereby we scrub all the data to check it's there, and we re-replicate it as needed to ensure that we hold customer data securely. But glass isn't like that. Glass holds the data without bit rotting. So it's very good for these long-term storage scenarios. It's also a very cheap media. It's very easy to get large quantities of glass at very low cost. And I like to think of the media as a seekable media. By that I mean that you can reach any part of the glass very easily by focusing in the volume or by moving the piece of glass to the right place. So it's, you can compare it against, say, a tape, which is not really a seekable media. It takes a long time to move around a piece of tape. It's very fast to move around glass. And lastly, I think the key benefit of glass is that you can pour your data in, and then you don't need to be continuously rereading it on a 5 to 10 year time scale to bring it up to date with the latest standards of data encoding. So you can write it once, leave it in place, read it forever. So really, glass gives us the permission, the opportunity to rethink the new media for a new setting. One of the other nice things about these systems is that it allows us to disaggregate the system. If you think of a traditional hard drive, you buy the hard drive, it comes with platters in the drive, but it also comes with read and write heads. You buy it as one unit, and you can't change the ratio between the media, the read, and the write. However, with these library systems, you have a set of read heads, you have a library area where you store your media, DNA or glass, and you have a read system where you have one or more read heads to read the data out. And you can choose, over different periods of time, how many read heads to put in, how many write heads to put in, how much capacity to put in. So this gives you far more flexibility in deploying and managing the system than you would with systems like hard drives. So what does it look? What's changed about glass media that makes it possible today? Well, what's changed is that femtosecond lasers are now readily available. I'm showing you here two microscope images. On the left, you can see there's quite a large amount of cracking. This sample was written with a picosecond laser. A picosecond is 10 to the minus 12 seconds. Sounds like a short length of time, but this is actually quite a lot of energy going into the glass and causing these cracks. We can't use that to store data. That's far too disorganized. In contrast, much nicer on the right, we've got a sample written with a femtosecond laser, 10 to the minus 15 seconds. Here, we're able to precisely control the amount of energy going into the glass to get these lovely regular voxels, and we can store data in there. So how do we do it? Well, we use pulses from these femtosecond lasers. We focus them into the bulk of the glass, and at the beam focus, the voxel forms when we fire the laser. We then repeat that to write a whole 2D sector's worth of voxels, and then we can write several sectors in the bulk of the glass. And this is quite important because writing in the middle of the media means we automatically get some nice durability properties where the data is protected by this shield of glass around the media. Well, what do these nanogratings look like? This on the left is a scanning electron microscope picture of a single voxel sliced horizontally through it here. And you can see that these features at 20 nanometers are substantially smaller than the wavelength of light. And there's some multi-photon absorption process going on that allows us to create these very small structures. And the orientation of these lines actually depends on the polarization of the laser light going in, and we can read that back out again using a polarizing microscope in order to see what the polarization of those gratings are. So we get to store data in 5 dimensions. Here I'm showing you an arrangement of several voxels in 3 dimensions, so that's X, Y, and Z within the bulk of the glass. We get a 4th dimension, which is the direction or the orientation of these nanogratings, which we get to control. And the final 5th dimension is the length of these teardrop shapes, which we can also control. So that gives us 5 axes to play with. So it's naturally a multi-level encoding here, similar to DNA and its bases. What does writing look like? Well, here I'm showing you a small movie that we recorded looking through the microscope that we use for debugging our write system as the laser is firing pulses and we're moving the glass under the laser. And as the pulses fire, you occasionally see a sort of spark of light or a flash. That's happening is when the laser pulse is happening at the same time as the camera is actually open. And at that point, you get a proper flash. And so you can see that we're building up this pattern of dots on the glass. In fact, in the lab, we joke that we've basically built a really rather elaborate dot matrix printer. What does reading look like? Well, we put the glass under a microscope. Here on the right, you can see the microscope objective. You can see the sample underneath being moved around by a motorized stage under computer control, so we can seek to the various sectors. And as we focus through the depth of the image, the depth of the glass, we pick up multiple different layers of voxels. Here we're seeing about 15 layers or so. So in summary, glass is this lovely media that is cheap. It's very robust. It's got great low latency properties, and it's got an amazing lifetime. And so I think that it is an excellent candidate for the kinds of archive workloads that the M&E community really needs to think about. Another great way of storing data is in DNA, and my colleague Karin will now say something on that. Thank you.
So this project is a collaboration between Microsoft and University of Washington, and together we created a lab, the Molecular Information Systems Lab, to study how we can leverage biology and chemistry to the benefit of the IT industry. So storing digital information in DNA is the first such project we tackle, and it's motivated by the trends that Austin was showing in the beginning of his presentation, where we're seeing a huge explosion on data creation and how much data we create as a whole, as a population, and the amount of storage that's available to store that information. There is a gap, and that gap is growing. And so we think that to put a dent on this issue, we need radical new solutions, and we think DNA is one such solution. So let me tell you what makes DNA such an exciting medium for digital data storage. The first characteristic of DNA that we think is very attractive is its density. So here what I'm showing is a test tube. At the bottom of that test tube you see a pink smear, and in that pink smear we can store the equivalent of about 10 terabytes of data, just the bottom of the test tube. So the density is really fantastic. To give you another sense of what that density means, what I'm showing here is a data center. It's a cold storage data center. It houses about 1 exabyte of data, so 10 to the 18 bytes. It's about the size of 2 Walmart supercenters. If you were to scale how much DNA you'd need to store that information, it would be this size. And you can barely see it, but I promise it's really there. It's just 1 pixel under the arrow there. So if you were to look at it in real size, so building size, this would be how much DNA you'd need to store that 1 exabyte of information. So going from a building to a cubic inch, it's quite a mind-blowing change in the amount of information you can store. The other thing that makes DNA very compelling is its durability. So we see evidence of natural DNA, biological DNA, that lasted for thousands of years. I think the oldest piece of DNA that was ever read is 700,000 years old. Of course, it needs to be stored in the right conditions, but these conditions are not very difficult to replicate synthetically. So there's a group at ETH Zurich who's been able to encapsulate the DNA in silica and make it and demonstrate that it can last for about 2,000 years if kept in about 10 degrees, which is 50 Fahrenheit. It's not that difficult to keep. So that makes it very compelling. Another characteristic of DNA is that readers will never become obsolete because now we have the ability of reading DNA. We want to read biological DNA. We want to read our own DNA for clinical purposes, for example, and so we'll always be interested in reading it, and we'll always have readers to read the DNA. So the media doesn't become obsolete. Another characteristic that's very attractive, I think, for media and entertainment is that it's very easy to copy DNA. You can make millions of copies quite easily, and quite cheaply. So this seems like a nice property to have as well. So I told you why DNA is sort of an interesting medium. Now let me tell you how we store information in DNA. So if you remember from Biology 101, DNA is a double helix, so those are 2 chains of bases that are one of 4 types, A, C, T, and G. And the simplest way to think about it is just a sequence of arbitrary letters or bases. And so if we want to store a sequence of bits, if we want to store a sequence of bits, all we have to do is create a sequence of these letters or bases. And so here I'm showing a simple mapping, a nice way to think about it, even though it's not exactly how we really encode the data. But you can think of every 2 bits become one of these symbols, A, T, C, or G. So 0, 0 becomes A, 0, 1 becomes C, and so forth and so on. So all we have to do is to create sequences of these bases that encode the bits that we want to store. So the technology to create these sequences, to manufacture the sequences of DNA, and these are synthetic sequences of DNA, they're not biological DNA. We are really fabricating the sequences. The technology to do it allows us to create sequences that are about 150 to 230 bases long. So this can house about 10 bytes, and I'll tell you later how we deal with the fact that we can only store a small piece of information in each of these sequences. But bottom line here, what I want to say is that these, the DNA here is synthetic, so there's no cells, there's no life. We store the DNA dry, and that really increases the density at which we can store it. So here, what I'm showing is essentially our pipeline. So we start with bits, and we end up with bits on the way out. But in the middle, what we do is we take the bits, we'll translate into the sequences that we want to use to store the information. Then we'll synthesize the actual molecules that store that information and preserve it. There are multiple ways to encapsulate the DNA to make it last for a long time. I showed you one in one of the first few slides. The next step is we want to, if we want to read the information, is we need to access the information. We need to select which of the molecules that we want to read. We don't want to read our whole storage. We want to read pieces of it. It turns out that it's possible to do random access both physically and also chemically. And then we take those molecules we're interested in reading, we'll sequence them. The equipment that we use here is very similar to the equipment, or even many times the same equipment that's used in biotechnology to read biological DNA. We'll read them, we'll recover sequences, the likely sequences of bases that we've observed, and then we'll transform that back into bits, of course using error correction techniques to make sure that we fully recover the bits that we stored. So let's go one more level deep, and I'll show you how exactly we do this. So I told you earlier that we can store only about 10 bytes in a sequence of a DNA sequence. So what we have to do, if we wanted to store a video like this one, we actually did store in DNA. So this is an OKGo video, highly recommended, Rube Goldberg machine. We have to chop up that file into smaller pieces that we can then each encode into a particular sequence. So of course, in order to recover the data and know what goes where, we need to add a sequence number. So that's what we do, and this is not new in storage. Even with floppy disks, that was the case. And then we'll add some redundant data so that we can do error correction on the way out. Then we'll translate those sequences into sequences of DNA. And in addition to that, we add a file ID or some kind of data item ID so that we can chemically recover only data items that we're interested in reading on the way out. So once we have the sequences that we want to encode, the next step is really to fabricate those molecules. And so the fabrication technology essentially builds these molecules pretty much letter by letter from the ground up. And so it's like lawn growing from the ground. That's a good way to think about that. And multiple molecules with the same sequence are fabricated at the same time, and also molecules with different sequences are fabricated at the same time, and so there's parallelism in fabricating those molecules. So the next step is to preserve the DNA, and again, we're very focused on density, and so we'll remove the molecules from the substrate where they grew, and we'll really encapsulate them and make sure that they'll last for a long time. We'll store them into a library that could very much have the same form factor as tape, for example, and that could be then further stored into some kind of automated library. Now, talking about automation, that's very important for us. Of course, today in the lab, we do many of the things manually with test tubes and pipettes. But if we really want to use this as a storage solution, it needs to all be automated. So we've been studying different platforms to automate the whole process. And one of them is digital microfluidics. So this is essentially PCB. It's a computer board. I have one here in my pocket. Pretty simple. Pretty cheap technology. The droplets of water or other fluids that are carrying the DNA can be sandwiched between the board and that sheet of glass that you're seeing on top. And then we can use that platform to move these droplets containing DNA. We can mix droplets, and we can separate these droplets. We can do quite a few different operations with them that will help us automate the process. And so here it's a video that's just showing how easily we can move these droplets around, combine them, separate them, and really control them in a programmable manner. So I'll let it roll a little more. There's one more merge and split. So I don't know about you, but I find it pretty hypnotizing. So once we select the molecules that we want to read out, then we'll throw them into sequencers. So here I'm showing two examples of these sequences that will read the DNA. The one I'm showing on the left is desktop kind of reader. It's a pretty standard commercial product and has quite a bit of compute in it, and it uses optical technology to read the DNA. Now, most recently, what I'm showing here in the middle is another platform. It's based on what's called nanopore technology, where the DNA runs through literally a nanopore and causes current disturbances, and so you can electronically read the DNA that's going through and figure out what the sequences are. No matter what technology we use, we'll then obtain a bunch of reads that are electronic representations of the molecules that we've seen in these pieces of equipment. These reads, they come with errors. So there is quite a bit of errors that happen at the substrate level and at the both writing and reading level. And so we're going to use the error correction mechanisms that we put in place when we created these sequences to be able to read out the bits bit by bit with no errors. So this is what our pipeline looks like. We start with these reads from different files, different data items that we wanted to read. They come all mixed, so the first step is really to separate what belongs to each of the data items. And then once we have a data item that we want to decode, then the next step will be to select which of these reads are likely to have come from the same location in that original file. So we do clustering of those reads so that they're likely to have come from the same place. And the next step is, since each of them have errors in different locations, we'll do majority voting so that we can get a consensus on what the original piece of data was, or what the original sequence that we started with was. And if that's not enough, if we still have errors or if we still have missing sequences, we'll use that redundancy we added in the beginning to recover all the information that we had. And then we can translate that back into bits and recover our video. So this is, in a nutshell, what the DNA data storage pipeline looks like. So what have we done so far? So far, we've been able to store 400 megabytes of data, and we've been able to fully recover those bits with no errors at all. We've encoded a bunch of different types of media, just to show that if it can be encoded in bits, it can be encoded in DNA. And so we've encoded text from Project Gutenberg. We've encoded the Universal Declaration of Human Rights. We've encoded that OK Go video that I've been using as an example, databases from Crop Trust, and also archival quality songs from the Montreux Jazz Festival. And this effort, we've reported on this effort in Nature Biotech. It actually turns out to have been on the cover, so that was a very good surprise for us. And so this content that we've encoded is curated, but now one of the things we're doing is opening up to the public and letting you submit your own pictures. So if you have a picture you'd like to preserve in DNA, go to this URL and submit it there. More than welcome to receive. We're trying to collect 10,000 images that will then encode into DNA. So ultimately, the 400 megabytes is not a whole lot at this point, but every technology, every storage technology has to go through this milestone to be deployed at scale. So we hope to be on our way there. And ultimately, as researchers, our dream is to really create a system that we can put in a data center and offer a service so that the M&E industry can use and archive their really precious materials. So with that, I'll just close, and thank you very much for your time.